Close your eyes for a moment and listen not to the world around you, but to something far older, something almost unimaginable. What if I told you the universe has a voice? Not the silence of empty space we picture today, but a deep, resonant hum, a primordial song that has been traveling across the cosmos for nearly 14 billion years. This is the sound of creation itself, the vibrations left behind by the Big Bang, a cosmic fingerprint etched into the fabric of reality. And now, for the first time in human history, scientists are learning how to listen. This isn't just about curiosity, it's about rewriting the story of everything. Those first moments after the universe burst into existence weren't silent. They were alive with energy, a seething, roaring chaos of particles and waves crashing together in a symphony of heat and motion. Over time, as the universe expanded and cooled, those vibrations stretched into whispers, fading but never disappearing. Today, they linger as faint ripples in the cosmic microwave background, the afterglow of the Big Bang, and with cutting-edge technology, we're beginning to translate those ripples back into sound, reconstructing the very first notes of existence. Why does this matter? Because sound carries secrets. The pitch, the rhythm, the echoes of those ancient vibrations, they hold clues about how the universe formed, how galaxies took shape, even how the laws of physics themselves came to be. It's like finding a recording of the first words ever spoken, except this isn't just history, it's the foundation of reality. And as we peel back the layers of time, we're not just observers, we're time travelers, tuning into frequencies older than stars. So join me as we explore how science is turning cosmic echoes into music, and why this discovery changes everything we thought we knew about where we came from. The universe is speaking, and at last we're learning how to listen. Think of the cosmic microwave background as the universe's oldest photograph, a snapshot taken when everything was just a newborn, barely 380,000 years old. At that moment, the cosmos transformed from an opaque, superheated soup of particles into something transparent, releasing a burst of light that's been traveling ever since. But this light isn't just a relic, it's a message. Embedded within it are tiny variations, fluctuations in temperature no larger than a few millionths of a degree, and these imperfections tell a story. They're not random. These faint ripples are the frozen echoes of sound waves that once rippled through the early universe, back when it was so dense that vibrations could travel like sound through water. Picture dropping a pebble into a pond. The ripples spread outward, carrying energy. Now imagine that pebble is the birth of space-time itself, and those ripples are the first vibrations of existence. Over billions of years, those waves stretched with the expanding universe, imprinting their patterns onto the CMB like grooves on a cosmic record. Scientists decode these patterns much like linguists decipher an ancient script. The spacing between the ripples reveals how matter clumped together, seeding the galaxies and voids we see today. The pitch of those primordial sound waves, yes, they had a pitch, tells us about the pressure and density of the early cosmos. It's as if the universe left behind a musical score, and by measuring the notes, we can reconstruct its infancy. This is why the CMB isn't just a static image, it's a dynamic fingerprint. Some fluctuations are louder, others softer, some regions warmer, others cooler. Each variation is a clue pointing to forces we're still unraveling. Was inflation, the universe's explosive growth spurt, responsible for amplifying these vibrations? Do they hide traces of dark matter or even earlier, unknown physics? Every new map of the CMB brings us closer to answers. And here's the astonishing part. We're not just looking at the past, we're listening to it. By translating these temperature fluctuations into sound waves, researchers have recreated the universe's first audible hum, a deep, resonant drone that shifted into a chorus of higher tones as the cosmos expanded. It's a haunting melody, one that carries the weight of creation itself. So when we study the CMB, we're not just gazing at a picture, we're pressing our ears to the walls of time, hearing the echoes of everything that ever was or will be. Translating the universe's earliest whispers into something we can actually hear isn't just about playing scientist, it's an art form, a delicate dance between physics and creativity. Imagine you're handed a sheet of music, but instead of notes, it's filled with numbers, tiny variations in temperature, imprinted on the cosmic microwave background like Braille. This is where sonification comes in, the process of taking those silent, mathematical patterns and giving them a voice. The first step is understanding that light and sound aren't so different. Both are waves, just vibrating at different frequencies. The fluctuations in the CMB act like cosmic sheet music, with warmer spots representing higher pressure regions and cooler spots indicating lower pressure, essentially the crests and troughs of those primordial sound waves. Scientists take this data and assign pitches to the temperatures, stretching the waves back to their original frequencies before the universe's expansion slowed them to a near standstill. It's like rewinding a tape that's been playing for billions of years, speeding it up until the deep, distorted hum of the early cosmos becomes audible again. The tools they use are as fascinating as the sounds themselves. Advanced algorithms map the CMB's temperature variations to musical notes, often preserving the spatial relationships so that a cluster of hotspots might become a chord, while a long, cooler streak transforms into a sustained bass tone. Some teams even use radial sonification, where the data spirals outward from a central point, mimicking how sound waves would have radiated through the dense, early universe. The result isn't just noise, it's a haunting, resonant drone that shifts in pitch as you move across the sky, a direct echo of the universe's first vibrations. But why go through all this trouble when we could just study the numbers? Because sound reveals what visuals can't. Our ears are exquisitely tuned to pick up patterns and rhythms, subtle harmonies or dissonances that might be invisible in a graph. When researchers listen to the sonified CMB, they're not just hearing randomness, they're detecting the fingerprints of physics itself. The way matter clumped under gravity, the push and pull between dark energy and radiation pressure, even potential traces of phenomena we haven't yet named. It's like listening to a recording of a crowded room and suddenly picking out a single voice, a clue hiding in plain hearing, and the implications are staggering. By tuning into these ancient frequencies, scientists have already confirmed predictions about the universe's composition, like how ordinary matter makes up just 5% of the cosmic pie. But there are still mysteries lurking in those tones. Could certain harmonics hint at undiscovered particles? Might the faintest echoes reveal flaws in our theories of inflation? Every new sonification is like adjusting the dial on a cosmic radio, searching for stations we didn't know existed. This isn't just about nostalgia for the Big Bang. It's a reminder that the universe isn't silent, it's been singing since the beginning, and we're finally learning the words. That deep, resonant drone you're imagining, it's not science fiction. It's the actual sound of the universe in its infancy, a bass note so low it would shake the stars if we could hear it roar. Scientists have reconstructed these primordial vibrations, and what they've uncovered is a symphony unlike anything on Earth. Picture the lowest pipe on a cathedral organ, then drop it several octaves further, into a register so deep it vibrates your bones more than your ears. That's the baseline tone of the early cosmos, a fundamental hum born from the universe's own expansion, stretched impossibly low by billions of years of cosmic inflation. But here's the catch. These original frequencies are far below what human ears can detect. The sound waves that rippled through the early universe were about 57 octaves too deep for us to hear naturally. To put that in perspective, if the lowest note on a piano is 27.5 Hz, the universe's first note would be a vibration with a wavelength longer than the observable cosmos itself. That's why researchers don't just listen, they translate. Using sophisticated algorithms, they speed up these ancient vibrations by a factor of roughly 100 septillion, compressing billions of years into mere seconds. Only then does that cosmic heartbeat emerge from the silence, revealing a soundscape both eerie and beautiful. What does it actually sound like? Close your eyes and imagine standing in the center of a massive, hollow sphere as it resonates with a pressure that's almost physical, a drone so deep it feels like gravity itself is humming. Then, layered atop that foundation, subtle fluctuations rise and fall like a distant storm. These aren't random noises, they're the acoustic fingerprints of quantum fluctuations from the Big Bang, the seeds of all structure in the universe. Some reconstructions resemble Tibetan singing bowls crossed with the pulsing rhythms of industrial machinery, while others evoke the deep space radio static heard in sci-fi films, except this is real. The most astonishing part, these sounds aren't just artistic interpretations, they're direct sonic translations of hard data from the cosmic microwave background, with every shift in pitch corresponding to actual variations in the early universe's density. Warmer regions produce higher tones, cooler regions lower ones, creating a celestial melody that encodes the universe's DNA. When you listen to these recordings, you're not just hearing a simulation, you're witnessing the universe's first vibrations, painstakingly remastered for human ears. And the implications go beyond curiosity. These sounds act as a diagnostic tool, helping scientists test theories about the universe's composition. The timbre of those primordial tones, for example, confirmed the precise mix of ordinary matter, dark matter, and dark energy. Unexpected harmonics might someday reveal hidden dimensions or cracks in Einstein's relativity. It's as if the cosmos left us a voicemail from its birth, and we're only now learning how to play it back. So the next time you hear a deep bass note or the rumble of thunder, remember, you're catching an echo of the universe's first and oldest song. Einstein once described gravity not as a force, but as the bending of spacetime itself, a cosmic fabric warped by mass and energy. Little did he know his equations would one day help us hear the universe's birth cries. General relativity didn't just revolutionize our understanding of black holes or the bending of light. It quietly predicted the existence of gravitational waves, ripples in spacetime that carry energy across the cosmos. And these waves are more than cosmic messengers, they're the missing link between the silent equations on a chalkboard and the roaring symphony of the early universe. Think of spacetime as a vast, invisible drumhead. When massive objects like colliding black holes strike it, they send shockwaves vibrating outward at the speed of light. But in the universe's first moments, spacetime wasn't being struck by objects, it was the object. Quantum fluctuations, those tiny, random variations in energy at the smallest scales, acted like countless microscopic drumsticks, tapping the fabric of reality itself. According to relativity, these fluctuations didn't just vanish, they stretched and amplified as the universe expanded, imprinting their rhythms onto the cosmos like grooves on a record. Here's where it gets even more fascinating. Those primordial gravitational waves didn't travel alone. They interacted with the dense plasma of the early universe, creating pressure waves, literal sound waves, that pushed and pulled matter into clusters. Picture dropping a stone into a pond, but instead of water, the ripples are made of particles and radiation, their motion dictated by Einstein's equations. Over time, these sound waves froze into the cosmic microwave background's temperature patterns, leaving behind a sonic fingerprint we can now decode. The real magic lies in how perfectly relativity's predictions match what we observe. Einstein's math suggested that spacetime could vibrate, but it took a century for technology to catch up. When researchers finally detected gravitational waves in 2015, they confirmed not just the existence of these ripples, but their role in shaping the universe's structure. The same physics that governs colliding neutron stars also explains why the CMB's fluctuations aren't random noise. They're the echoes of relativity in action, a cosmic feedback loop where warped spacetime sculpted sound, and sound sculpted the galaxies. Yet some of the most profound insights come from where Einstein's theories meet their limits. Those earliest gravitational waves, born during cosmic inflation, might carry clues about quantum gravity, a realm where relativity and quantum mechanics collide. By studying the universe's first vibrations, we're not just testing Einstein's ideas, we're probing the edges of known physics, listening for whispers from a time before time. So when you hear that deep, reconstructed hum of the early cosmos, remember, you're not just hearing sound, you're hearing spacetime itself ring like a bell, a testament to the genius who first imagined the fabric of reality could sing. To understand how sound waves from the early universe could imprint themselves across billions of light years, we need to rewind to the most dramatic growth spurt in cosmic history: inflation. Picture this: in less than a trillionth of a second, the universe expanded faster than the speed of light, stretching from smaller than an atom to nearly the size of a grapefruit. This wasn't just expansion, it was spacetime itself unraveling at an unimaginable pace, and it did something extraordinary to those primordial sound waves. Before inflation, the universe was a seething, chaotic place where quantum fluctuations created tiny ripples in the dense particle soup. These ripples were the seeds of sound, vibrating at frequencies far too high for us to hear. But as inflation kicked in, it didn't just stretch space, it stretched those vibrations too, pulling them from microscopic whispers to cosmic-scale reverberations. Imagine plucking a guitar string so violently that its vibrations slow from a high-pitched twang to a deep, resonant hum. That's what inflation did to the universe's sound waves, freezing their patterns into the fabric of reality. This is why the cosmic microwave background isn't uniform. Those subtle temperature variations, the warmer and cooler spots we see, are essentially fossilized sound waves, stretched so thin by inflation that they became imprinted across the entire observable universe. The spacing between these fluctuations acts like a ruler, revealing the maximum distance sound could travel before the universe cooled enough to freeze them in place. Scientists call this the sound horizon, and it's one of the most precise measuring sticks we have for understanding cosmic evolution. But inflation didn't just preserve these waves, it amplified them. Quantum jitters that would have remained insignificant were suddenly blown up to cosmic proportions, creating the density variations that eventually collapsed into galaxies and galaxy clusters. Without inflation, those early sound waves might have faded into oblivion, leaving the universe smooth and featureless. Instead, they became the blueprint for everything we see today, from the largest voids to the tiniest stellar nurseries. Here's where it gets even more fascinating: the specific patterns we see in the CMB, the way those sound waves are distributed, act like a fingerprint for inflation's physics. The strength of the fluctuations, their size distribution, even the slight asymmetry between hotter and cooler regions. All of these are clues about how inflation works. Was it a single, violent burst, or did it happen in fits and starts? Did spacetime stretch uniformly, or were there wrinkles left behind? The answers are hidden in those acoustic patterns, waiting to be decoded. And the implications go far beyond cosmology. If we can pin down the exact nature of inflation, we might finally understand what triggered it, whether it was a field of exotic energy, a collision of higher dimensional brains, or something even more bizarre. These aren't just abstract ideas. They're the keys to understanding whether our universe is one of many in a vast multiverse, or if the laws of physics we know are just a local accident. So when scientists study those faint ripples in the CMB, they're not just mapping the past, they're reading the universe's birth certificate, written in the language of stretched sound waves. And every new observation brings us closer to answering the ultimate question: how did everything we know and everything we are begin? Mapping the faint whispers of the early universe requires instruments of extraordinary sensitivity, and none have been more revolutionary than the Planck satellite. Launched in 2009 by the European Space Agency, this space telescope spent 4.5 years staring into the depths of space, capturing the cosmic microwave background with unprecedented precision. Its mission was simple in concept but staggering in ambition: to photograph the afterglow of the Big Bang with such clarity that even the tiniest fluctuations, variations smaller than 1 part in 100,000, would be revealed. What Planck found transformed cosmology. Its map of the CMB wasn't just a static image, it was a cosmic treasure trove packed with clues about the universe's age, composition, and even its ultimate fate. By measuring the slight temperature differences across the sky, Planck calculated the universe's age with razor-sharp accuracy: 13.8 billion years, give or take a mere 40 million. That's like measuring the distance from New York to Los Angeles with an error no wider than a human hair. But Planck's revelations didn't stop there. Its data confirmed that ordinary matter, the stars, planets, and everything we can see, makes up just under 5% of the universe. Dark matter, that mysterious substance that binds galaxies together, accounts for 27%. The rest, dark energy, the enigmatic force accelerating the universe's expansion. These numbers might sound abstract, but they're the foundation of modern cosmology, and Planck's measurements pinned them down with unshakable certainty. Perhaps most astonishing was how Planck's findings challenged some long-held assumptions. The satellite's data revealed subtle anomalies in the CMB regions where the temperature fluctuations didn't quite match predictions. One hemisphere of the sky is slightly warmer than the other, and there's a mysterious cold spot that defies easy explanation. These quirks might seem insignificant, but in a universe that's supposed to be uniform on large scales, they're like finding fingerprints where none should exist. Could they hint at new physics or even evidence of other universes? The debate is far from settled. Yet Planck's legacy extends beyond raw data. Its observations have become the backbone of modern sonification projects, providing the most accurate sheet music for the universe's primordial hum. Researchers take Planck's temperature maps and translate them into sound, assigning pitches to fluctuations with such precision that we can now hear the universe's structure in ways graphs alone could never convey. Those slight asymmetries in the data, they become dissonant chords in the cosmic symphony, subtle but haunting deviations from what we expected. The satellite's work also settled a long-standing argument about the universe's geometry. By measuring the spacing between acoustic peaks in the CMB, the frozen remnants of those early sound waves, Planck confirmed that space is flat to within a fraction of a percent. This might sound trivial, but it has profound implications. A flat universe suggests infinite expansion, with matter and energy perfectly balanced to prevent either catastrophic collapse or runaway dissipation. It's a delicate equilibrium, one that Planck's data revealed with breathtaking clarity. Today, Planck's maps are more than just scientific artifacts. They're the Rosetta Stone of cosmology, helping decode everything from the birth of galaxies to the nature of dark energy. And as new missions like the James Webb Space Telescope peer even deeper into the cosmos, they build on Planck's foundation, testing its conclusions and probing its mysteries. The satellite may have ended its mission in 2013, but its voice still echoes through every discovery about our universe's origins. It's a reminder that sometimes, to understand the cosmos, we don't just need to look, we need to listen. Deciphering the universe's first sounds isn't like tuning into a clear radio station, it's more like trying to hear a whisper in a hurricane. Galactic dust, the fine particulate matter floating between stars, acts as cosmic static, scattering and absorbing the very signals we're desperate to capture. Imagine listening to a symphony through a wall of thick fabric. The melody is there, but muffled, distorted, its sharpest edges smoothed away. That's what happens when dust from our own Milky Way contaminates observations of the cosmic microwave background. Scientists spend years painstakingly subtracting this interference, peeling back layer after layer of modern noise to reveal the ancient hum beneath. Then there's the problem of missing pieces. Our view of the CMB isn't a perfect sphere, it's more like a patchwork quilt with ragged edges. The Milky Way's bulk blocks nearly 20% of the sky from clear observation, creating blind spots in our cosmic hearing test. And while space telescopes like Planck mapped vast swaths of the universe, even their precision has limits, tiny gaps in data to leave room for uncertainty, like trying to reconstruct a Beethoven symphony when every 10th note is randomly erased. Researchers fill these voids with statistical models and cross-referenced observations, but some nuances inevitably slip through the cracks. Theoretical challenges run even deeper. The equations governing how sound waves propagated in the early universe rely on assumptions about the exact mix of matter and radiation, the behavior of dark energy, even the topology of spacetime itself. If any of these assumptions are slightly off, the music we reconstruct could be out of tune. It's akin to finding an ancient instrument with no manual. We can guess how it was played, but until we uncover more clues, some harmonies remain speculative. Yet perhaps the most tantalizing obstacle is the silence we can't explain. Certain frequencies predicted by inflation models simply aren't appearing in the data as strongly as expected. Are these missing notes evidence of unknown physics, like extra dimensions or exotic particles? Or do they reveal flaws in our understanding of how sound waves interacted with the universe's expansion? Like archaeologists puzzling over gaps in a fossil record, cosmologists are left to wonder if the absences are accidents of preservation or signatures of something revolutionary. Despite these hurdles, the scientific ingenuity at play is staggering. To combat noise, teams use component separation algorithms that can distinguish between primordial signals and modern interference with eerie precision, like software that isolates a single voice in a crowded stadium. For theoretical uncertainties, they run thousands of simulations, tweaking variables to see which versions best match the observed CMB patterns. And when data is incomplete, they turn to complementary techniques, like measuring galaxy distributions, which act as cross-checks on the cosmic sound waves. The result isn't just incremental progress. Each challenge overcome sharpens our cosmic hearing, bringing those first vibrations into clearer focus. What once seemed like irrecoverable noise is now a treasure map, its gaps pointing toward deeper mysteries. After all, if reconstructing the universe's oldest sounds were easy, we'd have nothing left to discover. The static isn't just interference, it's the universe reminding us how much we still have to learn. The universe's oldest sounds might seem alien, but their echoes resonate with familiar rhythms here on Earth. Take black holes. When two of these cosmic giants collide, they don't crash silently. The event sends gravitational waves rippling through space-time, vibrations so powerful they're detected billions of years later as a faint chirp by observatories like LIGO. That sound isn't so different from a pebble dropped into a pond, just scaled up to cosmic proportions. Both are waves carrying energy, one through water, the other through the fabric of reality itself. Then there's the deep, resonant hum of the early universe, a bass note so low it defies human hearing. Yet we encounter something eerily similar in the ocean's abyssal zones. Hydrophones placed miles underwater pick up ultra-low frequency sounds generated by massive water pressure and shifting tectonic plates. These tones, sometimes lasting for minutes, mirror the stretched-out vibrations of primordial sound waves in the infant cosmos. Both are reminders, whether in the depths of space or the sea, vibration is a universal language. Even the structure of the cosmic microwave background finds earthly parallels. The CMB's temperature fluctuations, those frozen sound waves, create patterns resembling concentric circles, much like ripples from a stone tossed into a lake. Scientists call these acoustic peaks, and they're not just visual artifacts. They behave like the standing waves in a musical instrument, where certain frequencies amplify while others cancel out. Picture blowing across the mouth of a bottle to produce a tone. The early universe did something similar, with space-time itself as the instrument. The connections go deeper. When volcanoes erupt, they produce infrasound, frequencies too low for human ears but detectable across continents. These waves bend around obstacles and travel vast distances, just like gravitational waves curve around galaxies. Both are reminders that energy refuses to be silenced, whether it's a volcano's roar or a neutron star's collision. What ties all these phenomena together? Scale. A black hole merger might release more energy than all the stars in the Milky Way, while a raindrop splash is infinitesimal by comparison. Yet both speak the same physical language, vibrations echoing through their respective mediums. The universe doesn't discriminate between the colossal and the minute. A sound wave is a sound wave, whether it's shaking space-time or rippling through air. This universality isn't just poetic, it's practical. By studying how sound behaves in oceans or atmospheres, scientists refine models of cosmic acoustics. Laboratories use plasma chambers to simulate the dense soup of the early universe, observing how waves propagate in conditions mimicking the Big Bang's aftermath. Even musical theory plays a role. The harmonics detected in CMB data are analyzed using techniques borrowed from audio engineering, treating the cosmos as the ultimate synthesizer. So when you hear thunder rumble or feel the bass vibrate in your chest at a concert, you're experiencing a fragment of the same physics that shaped the universe. The cosmos isn't just out there, it's in the everyday sounds we often take for granted. A reminder that the universe's first song never truly ended, it just changed keys. At the universe's birth, the cosmos wasn't just hot and dense. It was alive with quantum chaos, a seething ocean of particles popping in and out of existence faster than light could cross an atom. These weren't mere ripples, they were the raw material of reality itself, fluctuations so tiny they'd vanish in a blink. Yet they held the blueprint for everything we see today. Quantum mechanics tells us that empty space is never truly empty. It's a frothing sea of virtual particles. And in the first fraction of a second after the Big Bang, this quantum noise became the universe's first composer. How does randomness on such a microscopic scale translate into the cosmic symphony we detect in the CMB? Picture a calm pond struck by a sudden rainstorm. Each raindrop creates its own tiny ripple, but over time, those ripples overlap and amplify, forming larger waves. In the early universe, quantum fluctuations acted like those raindrops, imprinting minuscule variations in energy density across the primordial plasma. But here's the twist: inflation, the universe's explosive expansion, stretched these quantum jitters from subatomic scales to cosmic proportions. What began as fluctuations smaller than a proton ended up spanning light years, their patterns frozen into the fabric of space-time like grooves on a record. The real magic lies in how these quantum seeds grew into sound waves. As the universe cooled, regions of slightly higher density created by those initial fluctuations pulled in more matter through gravity, while lower density regions expanded outward. This push and pull generated pressure waves, literal sound waves that traveled through the hot plasma at half the speed of light. And just like sound in air, these waves had peaks and troughs, areas where matter compressed and rarefied, creating the hot and cold spots we now see in the CMB. But quantum mechanics didn't just supply the seeds, it dictated the music, the spacing of those acoustic peaks in the CMB. That's a direct echo of quantum probabilities, a statistical fingerprint of how likely certain fluctuations were to arise. The universe wasn't playing random notes, it was following a score written by the laws of probability, with inflation as the conductor amplifying certain harmonies over others. This interplay between quantum randomness and cosmic structure solves one of cosmology's oldest puzzles: why the universe isn't perfectly smooth. Without those initial quantum fluctuations, gravity would have had nothing to work with, no dense regions to collapse into galaxies, no voids to stretch into cosmic emptiness. The stars, planets, and even us were all the result of quantum noise amplified across 14 billion years, a reminder that the largest structures in existence owe their existence to the smallest. Yet mysteries remain. Why do some fluctuations appear stronger than others? Could certain patterns hint at physics beyond the standard model, like supersymmetry or extra dimensions? Every new observation of the CMB is like tuning into a distant radio station, searching for static that might reveal new fundamental truths. The quantum origins of cosmic sound aren't just a historical curiosity. They're a living laboratory, testing our deepest theories about how reality works. So when you look up at the night sky, remember, the galaxies above aren't just scattered randomly. They're the crescendos of a quantum melody, a song that began as a whisper in the void and grew into the symphony of the cosmos. And with each new discovery, we're learning to hear more of its verses. Those first primordial vibrations did more than just echo through the cosmos, they built it. Every galaxy, every star, every planet owes its existence to the subtle variations in density created by those ancient sound waves. Picture the early universe as a vast, simmering cauldron of particles, where regions of slightly higher density acted like cosmic gathering points, pulling in more matter through gravity's relentless tug. These weren't random clumps, they were the direct descendants of acoustic peaks, the frozen remnants of sound waves that once rippled through the plasma. The process began with something astronomers call baryon acoustic oscillations. As sound waves traveled outward from denser regions, they pushed matter into spherical shells, like ripples expanding from a stone dropped in a pond. But when the universe cooled enough for atoms to form, around 380,000 years after the Big Bang, those waves suddenly froze in place. What remained were concentric rings of matter over dense regions surrounded by slightly emptier voids, all spaced at a predictable distance determined by how far sound could travel before the cosmic music stopped. Fast forward billions of years, and those subtle density variations became the scaffolding for everything we see today. The overdense regions grew into galaxy clusters, while the voids stretched into the empty expanses between them. This isn't just theory. Modern sky surveys have actually mapped this pattern, revealing a cosmic web where galaxies align along the same acoustic shells imprinted in the early universe. It's as if we're seeing the faint outline of those first vibrations stretched across the heavens. But how did whispers become skyscrapers? The secret lies in dark matter. While ordinary matter, the stuff we're made of, was pushed around by those early sound waves, dark matter, unaffected by radiation pressure, began clumping together even earlier. These invisible halos acted like gravitational anchors, drawing in the baryonic matter once the sound waves faded. Over time, gas pooled in these dark matter wells, cooling and collapsing into the first stars and galaxies. The sound waves didn't just dictate where structure would form, they set the rhythm for its growth. The scale of this process is staggering. Those acoustic peaks we see in the symphony. They correspond to a characteristic distance of about 500 million light-years in today's universe, a cosmic yardstick astronomers used to measure expansion. Galaxy surveys show this signature everywhere, with clusters spaced at multiples of this distance, a direct echo of the universe's first resonant frequencies. It's like finding fossilized footprints and realizing they match the stride of a living giant. Yet the story isn't just about gravity winning in the end. Those early sound waves left another gift: coherence. Without their organizing influence, matter would have clumped chaotically, leading to a universe where galaxies formed in random, isolated patches. Instead, the acoustic oscillations created a synchronized large-scale structure, a vast interconnected network where filaments of galaxies stretch across billions of light-years, following patterns set in motion before the first stars flickered to life. This interplay between sound and structure solves one of cosmology's deepest puzzles: why the universe looks the way it does. The Milky Way isn't floating in isolation. It's part of the Laniakea supercluster, a sprawling collection of galaxies all moving toward a common gravitational center. And this supercluster, like all others, traces its lineage back to those first density variations, the ones that began as whispers in the plasma. So when we map the cosmic web today, we're not just charting galaxies, we're reading a musical score written 14 billion years ago. The universe didn't build itself at random. It sang itself into existence, one vibration at a time, and we're living in the harmony that followed. Astro-Coustics might sound like science fiction, but it's one of the most revolutionary ways we're learning to understand the cosmos. This emerging field doesn't just study space, it listens to it, translating the vibrations of stars, the hum of interstellar gas, even the atmospheric echoes of distant exoplanets into a symphony of data. The idea isn't entirely new. Centuries ago, Pythagoras imagined the music of the spheres, a celestial harmony produced by planetary motion. Today, we're turning that poetic vision into scientific reality, using tools so precise they can detect the faintest cosmic whispers. The pioneers of Astro-Coustics come from unexpected backgrounds. Take astronomer Donald Kurtz, who realized that the pulsations of certain stars' subtle brightness variations could be converted into audible sound waves. These weren't arbitrary notes, they revealed the star's internal structure, like a musical fingerprint. Then there's physicist John G. Kramer, who sonified the cosmic microwave background, turning temperature fluctuations into a deep, resonant drone that echoes the Big Bang itself. These researchers didn't just analyze data, they taught us to hear it, unlocking patterns invisible to traditional telescopes. Modern astroacoustic tools are just as fascinating. Heliosismology, for example, studies the sun's surface oscillations to map its hidden interior, much like geologists use seismic waves to probe Earth's core. Spacecraft like NASA's Kepler mission have detected starquakes of vibrations in distant stars that reveal their age, composition, and even the potential habitability of their orbiting planets. And then there's the work being done with exoplanets. By analyzing how sound waves travel through an exoplanet's hypothetical atmosphere, scientists can infer its density, chemical makeup, and weather patterns, all without ever leaving our solar system. The implications stretch far beyond curiosity. Astro-Coustics offers a new way to test theories about stellar evolution. The sound of a young, turbulent star differs dramatically from an older, calmer one, providing clues about how stars age. In galaxy clusters, the movement of hot gas creates pressure waves that act like cosmic sonar, helping astronomers measure distances and map dark matter. Even black holes, long thought to be silent, produce detectable vibrations when they merge, a gravitational chirp that LIGO first captured in 2015. What makes this field so transformative is its accessibility. You don't need a PhD to appreciate the eerie beauty of a star's pulsations translated into music, or the rhythmic pulses of a binary star system. Public projects like the Sonification universe allow anyone to explore cosmic data through sound, blurring the line between science and art. It's a reminder that the universe isn't just something we see, it's something we experience. Astro-Coustics is still in its infancy, but its potential is boundless. Future missions plan to listen for atmospheric echoes on potentially habitable worlds, or decode the vibrations of neutron stars to test Einstein's relativity under extreme conditions. Some researchers even speculate that advanced civilizations might use sound-based communication, leaving detectable acoustic signatures in interstellar plasma. Whether these ideas pan out or not, one thing is clear: the cosmos is full of voices we're only beginning to hear, and as Astro-Coustics grows, it won't just expand our knowledge, it will change how we feel about our place in the universe. The stars have been singing all along. Now, finally, we're learning their language. Some people imagine the Big Bang as a deafening explosion, a Hollywood-style boom echoing through space. But here's the twist: space was so dense back then that sound waves couldn't even propagate the way we think of them today. What we call the sound of the early universe isn't something you could have stood there and heard with your ears. It's a pressure wave, a ripple moving through the hot, soupy plasma that filled everything. Think of it more like the vibration you feel when a subway passes underground, a physical pulse, not an audible noise. Then there's the myth that the universe has a single, true sound waiting to be uncovered, like some celestial melody hidden in the static. In reality, the tones we reconstruct from cosmic microwave background data are translations, human interpretations of mathematical patterns. The universe doesn't have a soundtrack in the way a movie does. Those deep, resonant drones you hear in Sonifications, they're creative renderings, like turning a temperature map into music. The original notes were fluctuations in density and temperature, not literal pitches. Another common mix-up is treating gravitational waves as sound. While both are waves, gravitational waves ripple through spacetime itself, not through any medium like air or water. They're more like the tremors of an earthquake than the vibrations of a guitar string. When scientists convert gravitational wave data into sound for public outreach, they're speeding up frequencies our ears can detect, but that doesn't mean black holes actually go whoop when they collide. And let's tackle the idea that space is completely silent. It's true that in the near vacuum between stars, sound as we know it can't travel, but that doesn't mean there's no vibration. Plasma waves, magnetic oscillations, even the solar wind, all of these create rhythmic disturbances that, if you were floating in the right spot with the right instruments, you might feel as much as hear. It's not the silence of an empty room, it's the silence of a forest at night, teeming with imperceptible movement. The beauty of cosmic sound isn't in literal noise, it's in the patterns. Those fluctuations in the CMB, the rhythmic pulses of distant stars, even the gravitational wave chirps, they're all part of a grand vibrational language. Understanding them isn't about hearing the universe sing, it's about learning to read its hidden rhythms. So the next time you hear a sonification of the Big Bang, remember, you're not listening to a recording. You're witnessing a masterpiece of scientific translation where data becomes poetry. Ever notice how an ambulance siren sounds higher as it races toward you, then drops to a lower pitch as it speeds away? That familiar shift is the Doppler effect in action, and it's not just happening here on Earth. The entire universe is stretching in a way that alters sound, including the ancient vibrations left over from the Big Bang. But in space, the rules change. Instead of an object moving through a stationary medium, it's space-time itself that's expanding, carrying galaxies along with it like raisins in rising bread dough. This cosmic stretching does something extraordinary to the sound waves imprinted on the cosmic microwave background. It redshifts them, dragging their frequencies down into deeper, slower vibrations over billions of years. Here's how it works. When light or sound waves get stretched by the expansion of space, their wavelengths grow longer, shifting toward the red end of the spectrum, hence the term redshift. For the CMB, this means those primordial sound waves haven't just faded. Their very pitch has dropped by about 57 octaves since they first rang out. If you could have heard them back then, they would have been a screeching cacophony, vibrating at frequencies comparable to a high-powered laser. Today, after eons of cosmic expansion, those same waves resonate at frequencies far below what human ears could detect, a bass note with a wavelength longer than the observable universe. But redshift isn't just about making things quieter or deeper. It's a time machine. The amount of stretching tells us how much the universe has expanded since the waves were emitted. When we analyze the CMB's redshift, we're essentially measuring how much spacetime has stretched since the plasma of the early universe cooled enough to release that first burst of light. The deeper the redshift, the older the signal, and the further back we're peering into cosmic history. It's like listening to a record played at the wrong speed. The slower it goes, the more you know the music's been traveling a long, long time. This effect isn't uniform either. Some regions of the CMB show slightly stronger redshift than others, hinting at the universe's lumpy beginnings. Areas where matter was denser experienced subtle gravitational redshifts as photons climbing out of those deep cosmic wells lost energy, their wavelengths stretching even further. These variations are tiny, just a few parts in 100,000, but they're critical. They reveal where the first galaxies would eventually form, like cosmic breadcrumbs leading us back to the universe's blueprint. What's truly mind-bending is that redshift doesn't just affect light. Those primordial sound waves, they've been stretched too, their original frequencies warped by the expansion of space. The universe hasn't just gotten quieter, it's dropped into a lower key like a singer whose voice deepens over time. And just as musicians tune their instruments to match a concert pitch, cosmologists use redshift to tune their models, ensuring their simulations of the early universe match the stretched-out vibrations we observe today. So the next time you hear a siren whizzing past, remember, the entire cosmos is doing the same thing, not with sound, but with spacetime itself. Every vibration, every photon, every whisper from the early universe carries this imprint of expansion, a reminder that nothing in the cosmos stays static. The universe isn't just expanding, it's singing, and redshift is the slow, inevitable deepening of its voice. The early universe didn't just hum a single, monotonous note, it sang in rich, layered harmonies, a cosmic choir where each frequency carried secrets about the fabric of reality. Picture a grand pipe organ where pressing one key sends air rushing through dozens of pipes, each vibrating at different pitches to create a chord. The primordial plasma worked the same way, with countless sound waves overlapping and interacting, their combined vibrations encoding everything from the density of matter to the push and pull of dark energy. These weren't random noises, they were precise mathematical harmonies shaped by the laws of physics into a symphony of structure. Scientists call these overlapping patterns acoustic peaks, and they're the universe's equivalent of musical overtones. The first peak corresponds to the fundamental frequency. The distant sound could travel before the universe cooled and froze the waves in place. But just like a plucked guitar string produces higher harmonics, the early cosmos generated secondary peaks, echoes of the original vibrations that reveal even finer details. The spacing between these peaks acts like a cosmic barcode, with each line hinting at the universe's ingredients. A higher second peak, for example, suggests more ordinary matter, while the third peak's strength can betray the influence of dark matter's gravitational pull. What's astonishing is how these harmonics persist across time. The same patterns we see in the CMB's frozen waves also appear in the large-scale structure of today's universe. Galaxy surveys show clusters spaced at intervals matching those acoustic peaks, like a song played once in infancy and again in adulthood, slower but still recognizable. It's proof that the universe's structure isn't arbitrary, it's a direct consequence of those early vibrations, stretched but never erased by billions of years of expansion. Yet the real magic lies in the dissonances. Not all frequencies align perfectly. Some harmonics appear slightly muted, as if a few pipes in the cosmic organ were stuck. These anomalies hint at forces we're still unraveling, perhaps the ghostly influence of neutrinos, those elusive particles that slipped through the early plasma like ghosts through walls, subtly damping certain waves. Or maybe they're clues about dark energy's infancy, a faint imprint of the pressure it exerted even in the universe's first moments. This harmonic complexity also solves a puzzle: why the cosmos isn't a chaotic jumble. Without multiple frequencies interfering constructively, matter would have clumped unevenly, leaving vast regions barren. Instead, the interplay of waves created a delicate balance, like a conductor ensuring no section of the orchestra overpowers another. The result, a universe where galaxies weave into intricate filaments and voids, a tapestry woven from sound. So when cosmologists study these cosmic chords, they're not just listening for beauty, they're reverse engineering the universe's recipe. Each harmonic is a measuring cup, revealing the exact proportions of matter, radiation, and dark energy. And just as a musician tunes an instrument by ear, scientists refine their models until the theoretical harmonics match the observed ones, ensuring the symphony of the cosmos plays on key. The universe didn't just explode into being, it composed itself one resonant frequency at a time. To recreate the birth of the cosmos, scientists don't just rely on telescopes, they turn to supercomputers, building virtual universes from scratch. These aren't simple animations. They're mathematical playgrounds where billions of particles dance to the tune of gravity, radiation, and quantum mechanics, simulating how those first sound waves shaped everything we see. One of the most ambitious, the Illustris TNG project, starts with a digital cube of space 300 million light-years wide, packed with over 30 billion particles representing dark matter, gas, and stars. Then, with equations governing everything from nuclear fusion to magnetic fields, They press play watching as primordial vibrations stretch into galaxies over billions of simulated years. The secret lies in the code. Unlike a movie's CGI, these simulations solve physics problems in real time, calculating how sound waves propagate through the early universe's plasma. Each fluctuation, no matter how tiny, gets its own set of equations, tracking how it interacts with dark matter's invisible scaffolding or how it's amplified by cosmic inflation. The results are mesmerizing. Swirling filaments of gas condense into galaxies exactly where acoustic peaks predicted, while voids expand in sync with the CMB's cold spots. It's like rewinding a cosmic film reel frame by frame to see if our theories match reality. But simulations aren't just confirmations, they're discovery engines. When researchers tweak variables like the amount of dark energy or the timing of inflation, they create alternate universes. Some collapse too soon, others rip apart. Only a handful produce galaxies aligned like those we observe, a cosmic Goldilocks test revealing which theories hold water. Recently, a simulation called Cosmic Dawn pinpointed how early sound waves might have funneled gas into the first stars, while Millennium showed dark matter's gravitational pull harmonizing with baryon acoustic oscillations to weave the cosmic web. The challenges are as immense as the simulations themselves. Modeling quantum fluctuations at the Big Bang requires calculations so precise they'd take millennia on a home computer. Supercomputers like Summit at Oak Ridge National Lab crunch the numbers in weeks, using algorithms that mimic how sound waves dampen in turbulent plasma or how neutrinos subtly smear acoustic peaks. Even then, approximations are necessary. No machine can yet simulate every atom in a universe, but by focusing on key processes like how dark matter clumps or how hydrogen absorbs heat, scientists extract startlingly accurate echoes of those first vibrations. What's revolutionary is how these virtual universes listen. By converting simulated density fluctuations into sound, researchers compare their digital creations to sonifications of the actual CMB. If the pitches match, the physics is likely right. If they clash, it's back to the code. This feedback loop has already settled debates like confirming that dark matter must be cold, slow-moving to explain the observed harmonic patterns. Other simulations hint at wilder possibilities, like primordial black holes distorting sound waves or extra dimensions altering their propagation, the ultimate goal. A simulation so precise it can predict undiscovered phenomena, like relics from before inflation or the true nature of dark energy. Already, projects like Euclid and LSSD are feeding fresh observational data into these digital labs, refining the cosmic score note by note. It's a reminder that the universe's first sounds aren't lost to time, they're waiting to be replayed, one line of code at a time. Dark matter might be invisible, but it left an unmistakable imprint on the universe's first sounds. Think of those primordial sound waves rippling through the early cosmos. Ordinary matter, like protons and electrons, was pushed around by the pressure of radiation, creating peaks and troughs in the plasma. But dark matter, it didn't play by the same rules. Unaffected by light's push and pull, dark matter's gravity acted like an anchor, subtly tugging at those waves, bending their paths and altering how they echoed through space. The result, a cosmic duet where visible matter danced to the tune of radiation, while dark matter hummed its own gravitational bassline, warping the music in ways we can still detect today. Those distortions are written into the cosmic microwave background like sheet music. When scientists measure the spacing between the CMB's acoustic peaks, the frozen remnants of those ancient sound waves, they're not just seeing the imprint of ordinary matter. The peaks are slightly offset, their positions nudged by dark matter's invisible hand. It's like listening to a choir and realizing one singer is slightly off rhythm, not because they're out of tune, but because they're responding to a force no one else can see. That subtle mismatch is a smoking gun, revealing how much dark matter was present in the early universe and how it shaped the growth of structure. But dark matter didn't just shift the peaks, it changed their volume. Ordinary matter, buzzing with energy, produced loud, sharp fluctuations in the plasma. Dark matter, though, smeared those sharp edges, damping the wave's intensity in a way that left a telltale signature. The CMB's power spectrum, the graph that shows how strong different sound wave frequencies were, has dips and slopes that only make sense if dark matter was there, quietly smoothing out the chaos. Without it, the universe's sound waves would look wildly different, like a song missing its bass track. This isn't just about confirming dark matter exists. The precise way it altered those vibrations reveals its personality, how heavy its particles might be, how fast they moved in the early universe, even how they interacted with ordinary matter. Cold dark matter, for instance, leaves a cleaner acoustic signature than warm dark matter, which would have blurred the peaks more dramatically. By studying these patterns, cosmologists have narrowed dark matter down to something slow and massive, ruling out entire classes of theoretical particles. Yet mysteries linger. Some regions of the CMB show damping that's stronger than expected, hinting that dark matter might have quirks we haven't yet imagined, perhaps interacting with itself in ways beyond gravity, or leaving faint echoes of collisions from the universe's first second. Future telescopes, like the Simons Observatory, will listen for these whispers with even sharper ears, tuning into frequencies that could rewrite our understanding of the cosmos' hidden skeleton. So when you hear a sonification of the Big Bang's echoes, remember, you're not just hearing the birth of stars and galaxies, you're hearing the shadowy influence of the unseen, a reminder that the universe's loudest symphonies are often conducted in silence. The hunt for primordial gravitational waves is like searching for the faintest whisper in a thunderstorm, a signal so delicate it could rewrite our understanding of the universe's first moments. These ripples in space-time, predicted to have been generated during cosmic inflation, aren't just echoes of the Big Bang. They're the only direct evidence we might ever have of that explosive growth spurt. Imagine the universe stretching faster than light itself, quantum fluctuations magnified to cosmic scales, and space-time vibrating like a drumhead struck by unimaginable energy. Those vibrations never completely faded. They've been traveling for over 13 billion years, growing fainter but never disappearing, carrying secrets about how everything began. Detecting them isn't about listening in the traditional sense. Unlike the pressure waves in the early universe's plasma, gravitational waves warp the fabric of spacetime itself, stretching and squeezing distances as they pass. The ones we're chasing, primordial gravitational waves, are far weaker than the ripples from black hole mergers detected by LIGO. Their wavelengths are so vast they could span the observable universe, making them more like a slow, cosmic heartbeat than a sharp chirp. To catch them, scientists don't use microphones or telescopes. They turn to the cosmic microwave background, searching for a unique twist in its polarization patterns called B modes, a swirling imprint left by these ancient spacetime ripples. The stakes couldn't be higher. Finding these waves would be the smoking gun for inflation, confirming that the universe really did expand exponentially in a fraction of a second. It would also open a window into energies so high they're unreachable by any particle collider, offering clues about how gravity might unite with quantum mechanics. Some theories even suggest these waves could carry traces of phenomena before the Big Bang, hints of a multiverse or extra dimensions, but the search is fraught with challenges. The signal is buried under cosmic noise, dust in our galaxy, gravitational lensing, even the afterglow of later universe events. Projects like BICEP and the Simons Array have spent years scanning patches of sky near the South Pole, where thin, dry air reduces interference. In 2014, BICEP-2 thought they'd found the telltale swirls, only to realize galactic dust had mimicked the signal. It was a sobering reminder: the universe doesn't give up its secrets easily. Now, next-generation experiments are rising to the challenge. The Simons Observatory, with its 500,000 detectors, aims to map the CMB's polarization with unprecedented precision. Future space missions like Lightbird plan to scan the entire sky from orbit, above Earth's atmospheric distortions. And some researchers are exploring radical alternatives, like using pulsars as natural gravitational wave detectors. They're precisely timed radio beams subtly altered by passing space-time ripples. What keeps scientists going is the tantalizing possibility of hearing the universe's very first notes. If successful, we wouldn't just be validating a theory, we'd be tuning into a soundtrack older than stars, a vibration from the moment time began. And just like the first detection of gravitational waves from black holes, it could open a whole new way of observing the cosmos, turning space-time itself into a medium for discovery. The hunt isn't just about finding waves, it's about learning to listen to the universe in a way we never have before. Long before telescopes or satellites, humans looked to the stars and heard music. The ancient Greeks envisioned celestial spheres rotating in perfect harmony, singing as they moved. Pythagoras believed planets hummed in mathematical ratios, a cosmic scale we simply couldn't perceive. Today, we've turned that poetic intuition into something tangible. Composers and sound artists are weaving real astrophysical data into breathtaking musical works, giving voice to the universe's hidden rhythms. Take NASA, a collaboration with composer Sophie Kastner, who transformed data from the Chandra X-ray Observatory into an eerie, shimmering orchestral piece. The flickering light of distant pulsars became staccato violin notes, while the deep glow of nebulas morphed into resonant cello lines. It's not metaphor, it's translation, with every musical choice rooted in the actual frequencies and intensities of cosmic phenomena. Electronic musicians are equally captivated. Artist Diego Stocco famously recorded the vibrations of a 4.5 billion-year-old meteorite, using contact microphones to capture its metallic hum when struck. The result, an otherworldly percussion instrument, its tones literally forged in space. Meanwhile, projects like the Sonification universe take raw data, the spin rates of neutron stars, the radio emissions of Jupiter, and map them directly to synthesizers, creating pulsating soundscapes that feel both alien and strangely familiar. These aren't just artistic experiments, they're bridges between disciplines, proving that science and creativity speak the same language when it comes to the cosmos. Even classical traditions have embraced this fusion. Composer Terry Riley's Sun Rings, commissioned by NASA, incorporates recordings of solar wind plasma waves captured by spacecraft, weaving them into a choral and orchestral tapestry. The Kronos Quartet performed it with visuals of deep space imagery, creating a multisensory experience where audiences don't just hear the universe, they feel its immensity. Similarly, Anna Meredith's Anno integrates data from the European Space Agency's Planck satellite, converting temperature fluctuations in the cosmic microwave background into sweeping, dissonant harmonies that echo the universe's own discordant beginnings. What makes these works so powerful is their authenticity. When you listen to a sonification of Saturn's radio emissions, a haunting series of whistles and crackles caused by the planet's magnetic field interacting with solar wind, you're not hearing an artist's interpretation of space. You're hearing space itself, its raw vibrations transposed into human audible ranges. It's the difference between painting a portrait of someone and playing a recording of their heartbeat. One evokes, the other reveals. This cultural movement goes beyond concert halls. Mobile apps now let anyone play the Hubble Deep Field image, assigning pitches to galaxies based on their redshift. Schools use sonifications of solar flares to teach physics, proving that melody can be a powerful mnemonic for complex science. And on platforms like YouTube, millions have shared viral videos of the sound of a black hole, where NASA, a remix of pressure waves from the Perseus cluster, originally 57 octaves below human hearing, captivates audiences with its deep, groaning bass. Perhaps the most profound impact lies in how these works reshape our connection to the cosmos. Music bypasses intellect and speaks directly to emotion. When you hear the wobble of a distant exoplanet star translated into a melancholic piano motif, or the rhythmic pulses of a quasar turned into electronic beats, the universe stops being an abstract concept. It becomes alive, intimate, almost breathing. Composers aren't just creating music inspired by space, they're letting space create music through them. And in that act, we're reminded that the universe isn't a silent void. It's a symphony, and we're only beginning to learn its notes. Imagine a classroom where students don't just read about the Big Bang, they hear it. This is the power of sonification in education, turning abstract cosmic concepts into something tangible and unforgettable. Educators are harnessing the sounds of the universe to demystify astrophysics, from elementary schools to university lecture halls. Take redshift, for example. Instead of struggling to visualize how light stretches as space expands, students listen to a recording of a siren pitch shifted downward, mimicking how galaxies' light drops to lower frequencies as they race away from us. The Doppler effect goes from textbook diagram to aha moment as the classroom fills with the eerie, sliding tones of an expanding cosmos. But it's not just about analogies. Real data sonifications let students interact with the universe directly. A high school teacher might hand out audio files of the cosmic microwave background's fluctuations, asking students to identify patterns in the drone, warmer spots as higher pitches, cooler regions as deeper tones. Suddenly, the CMB isn't a static image on a screen. It's a dynamic soundscape where hotter and cooler areas form distinct musical intervals. One group in Colorado even coded their own sonification software, mapping star formation rates in nearby galaxies to percussive beats. Faster star birth equals quicker rhythms, transforming dry datasets into cosmic drum circles. The magic lies in accessibility. Complex ideas like inflation become intuitive when students hear a sound wave's pitch drop dramatically, simulating how quantum fluctuations were stretched by the universe's explosive growth. A middle school demo might use a synthesizer to play a high-frequency tone, then slowly lower the pitch while reducing its volume, mimicking how primordial sound waves faded into today's deep, near-silent hum. For visual learners, educators pair these sounds with interactive spectrograms, showing how the wave's frequencies shifted over billions of years. It's multisensory learning at its best: ears, eyes, and curiosity all engaged. University courses take it further, using sonification to reveal hidden relationships in data. Astronomy majors might analyze gravitational wave signals by ear, training themselves to distinguish the chirp of colliding neutron stars from the thud of black hole mergers. Others explore galaxy clustering through 3D audio, where headphones simulate moving through space. Clusters of galaxies ping louder as you approach them, their pitches revealing redshifts. These methods aren't gimmicks, they're rooted in research showing that sound can highlight data patterns even experts miss. One Stanford study found students who sonified exoplanet transit data identified anomalous dips in starlight, potential signs of undiscovered worlds 30% faster than those relying on visuals alone. Beyond classrooms, public outreach thrives on cosmic sound. Planetariums now host listening parties where attendees recline under domes, immersed in the pulsing rhythms of variable stars or the solar wind's crackle. Libraries loan Universe in a Box kits with tactile models and paired audio files, letting blind and low-vision learners feel 3D printed supernova while hearing their shockwaves translated into crescendos. Even podcasts weave sonifications into storytelling, like the BBC's Cosmic Vibration series, which scored episodes with melodies derived from asteroid rotation rates. The impact: a generation that sees and hears physics differently. A seventh grader who once struggled with graphs might later recall how galaxy filaments sounded like plucked bass strings, leading them to pursue astrophysics. A planetarium visitor could leave humming the harmonics of the CMB, realizing the universe isn't just math, it's music. And that's the ultimate lesson. By giving the cosmos a voice, we're not just teaching science. We're helping everyone, from kids to lifelong learners, feel like part of the universe's grand, resonant story. The next decade will transform how we listen to the universe, with cutting-edge instruments poised to capture cosmic vibrations with unprecedented clarity. At the forefront is the James Webb Space Telescope, already revolutionizing infrared astronomy, but its role in Astro-Coustics is equally groundbreaking. Unlike Hubble's visible light snapshots, Webb's infrared vision peers through cosmic dust, revealing the faintest whispers of the first galaxies forming. These ancient structures grew from the very density fluctuations we detect in the cosmic microwave background, meaning Webb isn't just showing us the past, it's letting us trace how those primordial sound waves evolved into the galactic symphony we see today. Its observations of early star clusters could reveal how acoustic oscillations influenced the spacing of the first stellar nurseries, like finding the grooves on a record that shaped modern galaxies. Then there's Lightbird, a Japanese-led mission set to launch in the late 2020s with one singular goal: to hunt for the faintest B-mode polarization patterns in the CMB, the telltale swirls left by primordial gravitational waves. While Bicep and Planck gave us hints, Lightbird sensitivity will be 50 times sharper, scanning the entire sky with cryogenically cooled detectors to filter out galactic noise. Imagine trying to hear a pin drop in a hurricane. Lightbird tech is the equivalent of noise-canceling headphones for the cosmos, isolating inflation's signature from the chaos of intervening space. If successful, it could confirm whether the universe's exponential growth was driven by a quantum field, a collision of higher dimensional brains, or something even more exotic. Meanwhile, the Simons Observatory in Chile's Atacama Desert is already online. Its array of 50,000 detectors mapping the CMB's polarization with microscopic precision. Unlike single-dish telescopes, this facility uses a fleet of small, synchronized receivers to cover vast swaths of sky, stitching together a high-resolution acoustic map. Its data will refine our measurements of the universe's sound horizon, the characteristic spacing between galaxy clusters, to within 1% accuracy, effectively tuning our cosmic piano to perfect pitch. But perhaps the most ambitious project on the horizon is CMB S4, a next-generation ground-based observatory planned for the 2030s. With telescopes at both poles and in Chile, it'll combine the stability of Antarctica's dry air with the wide-field views of the southern hemisphere, creating the most detailed recording of the early universe ever made. CMB S4 won't just listen, it'll dissect the harmonics of primordial sound waves with such precision that it could detect the imprint of hypothetical particles like actions, or even uncover evidence of a universe before the Big Bang. These missions share a common thread: They're not just upgrading our instruments, they're expanding our very definition of hearing. From space-based interferometers measuring gravitational waves to balloon-borne sensors floating above 99% of Earth's atmosphere, each tool brings us closer to answering existential questions. How did quantum fluctuations become galaxies? What triggered inflation? Is our universe one of many? The answers won't come as equations or images, but as vibrations subtle, ancient, and finally, unmistakably clear. The cosmic symphony isn't over. We're just getting better microphones. Who gets to own the sound of creation itself? As scientists transform cosmic data into audible experiences, a surprising debate emerges, one that straddles copyright law, cultural heritage, and the very nature of discovery. When NASA released sonifications of the Perseus galaxy cluster's pressure waves, the recordings went viral, but few paused to ask, can an agency claim intellectual property over vibrations that predate humanity? The question isn't hypothetical. In 2020, a musician sampled those black hole sounds in a hit song, sparking legal gray areas. Is this akin to copyrighting a bird's song? Or does the act of translating raw data into audible form constitute genuine ownership? Legal scholars are divided, with some arguing that cosmic phenomena should belong to the public domain as natural occurrences, while others note the labor and innovation behind sonification justifies protections. This tension extends beyond courtrooms. For indigenous cultures, the universe's sounds aren't just data, they're sacred narratives. The Maori tradition of Whakapapa, for instance, views celestial phenomena as part of an unbroken genealogical chain, where stars and planets literally speak to ancestors. Similarly, Aboriginal Australian songlines encode astronomical knowledge into oral traditions passed down for millennia. When Western institutions sonify the cosmos without consulting these communities, it risks reducing profound cultural touchstones to mere scientific outputs. Some observatories are now collaborating with indigenous elders, blending astrophysics with traditional knowledge to create interpretations that honor multiple ways of knowing. The Atacama Cosmology Telescope, for example, worked with local Atacamino communities to incorporate their cosmology into CMB research, yielding new metaphors for cosmic sound waves as the breath of the mountains. Yet even collaboration raises ethical quandaries. Who benefits when indigenous cosmologies help decode the universe's vibrations? While projects like the Navajo Nation's partnership with NASA on asteroid missions set precedents for shared credit, most sonification initiatives lack formal frameworks for compensation or co-authorship. The dilemma echoes broader debates about bioprospecting, where genetic research draws on traditional knowledge without equitable returns. As one Lakota astrophysicist noted, we've mapped the stars for generations. Now that science finally hears them, will it listen to the people who first sang their stories? Commercialization adds another layer. Startups now sell space sound albums, from Saturn's radio emissions to neutron star pulses, marketed as therapeutic or artistic experiences. While some profits fund further research, critics argue this monetizes the cosmos itself, turning shared heritage into premium content. The contrast is stark. The same vibrations revered as sacred by some become ambient sleep tracks for others. Even open access data can perpetuate disparities when communities lacking high-speed internet or technical training can't participate in sonification projects. The way forward may lie in redefining ownership altogether. Inspired by the Open Universe initiative, some propose treating cosmic sounds like Antarctica, a commons governed by international agreements where scientific access is balanced with cultural preservation. Others advocate for Creative Commons licenses that require attribution while allowing artistic reuse. What's clear is that as sonification bridges science and culture, it demands more than technical skill. It requires humility to recognize that the universe's voice isn't ours to claim, but to share, interpret, and above all, respect. Imagine strapping on a virtual reality headset and suddenly floating in the seething plasma of the early universe, surrounded by shimmering waves of pressure that pulse and ripple around you. This isn't science fiction, it's the cutting edge of astrophysics education, where immersive technology is turning abstract cosmic concepts into visceral experiences. Apps like Universe Sonification VR let users reach out and touch sound waves from the Big Bang, feeling their vibrations as they warp and stretch with the expansion of space. Each fluctuation corresponds to real data from the cosmic microwave background, mapped into 3 dimensions so you can literally move through the universe's acoustic fingerprint. Tilt your head and the pitch shifts, revealing how redshift warps frequencies over billions of years. It's a revelation that textbooks could never convey, physics made tangible. For those without VR gear, projects like Cosmic Vibrations bring the cosmos to your smartphone. Swipe across a timeline, and you'll hear the universe's sound waves evolve from a high-pitched screech in the first microseconds to the deep, resonant hum we detect today. Pinch to zoom into specific regions of the CMB map, and the app isolates those fluctuations as musical notes, letting you compose melodies from primordial density variations. Educators are already using it to teach Redshift students adjust sliders to stretch sound waves in real time, hearing first and how expansion alters pitch. One high school in Oslo even had students remix CMB data into electronic tracks, blending science with creativity to unforgettable effect. But the most groundbreaking work happens in planetariums. The Hayden Sphere in New York recently debuted Cosmic Acoustics, a full-dome experience where visitors don motion-tracked headphones. As you walk beneath the projected CMB, sound moves with you. Warmer regions emit higher tones from above, while cooler voids resonate with bass notes underfoot. The effect is uncanny, as if the universe itself is a surround sound system. Meanwhile, the Singing Telescope's installation in Tokyo syncs live data from radio telescopes to a generative music algorithm, turning the whispers of distant quasars into an ever-changing symphony. These tools aren't just for passive consumption. Platforms like Astrosonic invite users to manipulate variables. What if dark matter were warmer? What if inflation lasted longer? And instantly hear how those changes alter the cosmic soundtrack. It's a playground for curiosity, where tweaking equations becomes as intuitive as tuning a guitar. At MIT's Media Lab, researchers are even experimenting with haptic feedback vests that let deaf users feel cosmological sounds through vibrations, making the universe accessible in ways light years beyond traditional visuals. The democratization goes further with open-source projects. GitHub hosts dozens of code repositories where anyone can sonify NASA raw telescope data, from the rhythmic pulses of magnetars to the Doppler-shifted screams of hypervelocity stars. One community effort, Sonify the Sky, crowdsources interpretations of galactic surveys, yielding surprises like a volunteer who noticed harmonic patterns in galaxy clusters that algorithms had missed. It's proof that when you let the public listen, not just look, new discoveries emerge. What makes these experiences revolutionary isn't just their tech, it's their ability to bypass jargon and speak directly to intuition. A VR simulation of acoustic peaks doesn't need to explain baryon oscillations. You grasp their significance when you see and hear how their spacing predicts galaxy formation. A child playing with an app that turns supernova shockwaves into drumbeats isn't memorizing equations, they're internalizing the rhythms of stellar death. This is science communication at its most transformative, where the universe's oldest sounds become bridges across age, language, and background, and the frontier keeps expanding. Upcoming projects aim to let users step inside gravitational wave detections, feeling the space-time ripples from colliding black holes wash over them. Others plan to integrate EEG headsets, allowing your brainwaves to modulate cosmic sounds in real time, a feedback loop between mind and universe. The message is clear: astrophysics isn't just something we observe. It's something we experience, play with, and ultimately belong to. The cosmos has been singing for billions of years. Now, finally, we're learning to sing back. Human ears are fine-tuned for survival on Earth, not for eavesdropping on the cosmos. The very anatomy that lets us catch a whisper in a quiet room or the crash of ocean waves becomes useless beyond our atmosphere. Sound, as we experience it, requires molecules to vibrate, whether air, water, or solid ground. But space is a near-perfect vacuum, with particles so sparse that a scream would travel no further than your own skull. Even if you floated beside a colliding galaxy cluster, the event would play out in eerie silence, its cataclysmic energy radiating as light and gravitational waves, nothing for your eardrums to detect. Our biological limits run deeper. The average human hears frequencies between 20 and 20,000 Hz, a narrow window compared to the universe's acoustic range. The early cosmos produced pressure waves oscillating trillions of times per second, far higher than any bat's squeak or dolphin's click. Over billions of years, cosmic expansion stretched these vibrations into infrasound, dropping their pitch by 57 octaves. Today, the remnant hum of the Big Bang resonates at frequencies a million billion times lower than our hearing threshold, with wavelengths longer than the observable universe itself. It's not just that space is silent to our ears, it's singing in a register evolution never prepared us to perceive. Technology bridges this gap by acting as a cosmic hearing aid. Radio telescopes like ALMA capture electromagnetic waves from distant nebulae, which engineers transpose into audible frequencies, like slowing down a record played at the wrong speed. Sonification algorithms take this further, turning datasets into immersive soundscapes. When NASA translated the pressure waves from the Perseus galaxy cluster, they compressed 40 million years of oscillations into a few seconds of haunting groans, revealing patterns invisible in visual plots. Similarly, gravitational wave detectors like LIGO don't hear collisions directly but convert space-time ripples into chirps and thuds our brains can process. Yet even our machines face hurdles. Cosmic signals drown in noise, solar wind, galactic dust, even the faint heat of telescope electronics. Isolating primordial sound waves from the cosmic microwave background is like trying to identify a single voice in a stadium of roaring fans. Scientists combat this with interferometry, combining signals from multiple antennas to amplify faint whispers, or by launching observatories beyond Earth's atmosphere where the cacophony of our planet fades. The irony is poetic. The universe's grand symphony surrounds us, but perceiving it demands redefining what sound even means. From quantum vibrations stretched across eons to spacetime itself ringing like a bell, the cosmos speaks in dialects we're only beginning to decode. Our ears may be deaf to its true voice, but through ingenuity, we're learning to listen with new senses, transforming silence into song. The vibrations echoing from the dawn of time don't just fill in gaps in our cosmic maps, they shake the foundations of how we see our place in existence. If the universe has a voice, however metaphorical, what does it say about the nature of reality? Ancient philosophers from Pythagoras to Hindu Vedic scholars imagine the cosmos as an ordered symphony, a harmony of spheres where celestial movements followed mathematical rhythms. Today, we're uncovering something startlingly similar, not through mysticism, but through the frozen sound waves in the cosmic microwave background. The discovery that these vibrations follow precise acoustic peaks, like notes on a scale, forces us to confront an eerie possibility. The universe isn't just chaotic expansion. It's structured, almost musical in its design. This isn't just about physics, it's about meaning. When we listen to sonifications of the Big Bang's remnants, we're not hearing random noise. We're detecting patterns so consistent they've been called the acoustic signature of creation. For some, this raises spiritual questions. Could these vibrations be traces of an underlying order, a cosmic tuning that set the stage for life? Theologians and scientists alike grapple with the so-called fine-tuning problem, the observation that the universe's fundamental constants, from the strength of gravity to the mass of electrons, seem improbably perfect for our existence. Those primordial sound waves add a new layer. The very resonance of spacetime may have been calibrated to allow galaxies and ultimately us to form, yet the implications cut both ways. For every thinker who sees divine harmony in cosmic acoustics, another finds profound indifference. The universe's vibrations aren't melodies crafted for our ears, they're the byproduct of blind forces, the hiss of quantum fluctuations amplified by inflation. The music we detect is a cosmic accident, beautiful only because we've evolved to perceive patterns. This tension between purpose and randomness fuels debates from cosmology conferences to late-night dorm rooms. Does the universe hum with intention, or are we projecting meaning onto the static of an uncaring void? Perhaps the most humbling insight lies in the scales involved. Those sound waves traveled for billions of years before life emerged to hear them. Their existence doesn't depend on our perception. The cosmos rang with structure long before ears evolved to listen, suggesting a reality that transcends human frameworks. Indigenous cultures have long understood this, the Maori concept of Te Reo o Te Ao, the voice of the universe, or the Aboriginal songlines that map stars to terrestrial landscapes, both speak to a world alive with vibration, regardless of witnesses. Modern Astro-Coustics, in an unexpected twist, validates these ancient intuitions with data. The question isn't just whether the universe has rhythm, but what that rhythm reveals about existence itself. Every time we translate cosmic data into sound, we're not just doing science, we're engaging in an act of philosophical archaeology, digging through layers of noise to find the pulse of reality. Whether that pulse hints at deeper truths or simply mirrors our hunger for meaning, one thing is clear: the universe isn't silent. It's been speaking since the beginning. And in learning to listen, we're discovering not just how the cosmos works, but what it might be trying to say. When the first sonifications of the cosmic microwave background hit the internet, the reaction was electric. News headlines proclaimed, "Hear the sound of the Big Bang," while social media feeds flooded with awe-struck comments. Some listeners described the deep, resonant hum as hauntingly beautiful. Others called it the voice of God. Within hours, the audio clips went viral, racking up millions of plays as people shared their visceral reactions. One Twitter user confessed they'd played the CMB drone on loop to fall asleep, calling it the universe's lullaby, while a Reddit thread erupted with debates over whether the tone sounded more like a Tibetan singing bowl or the opening note of a sci-fi film score. The public wasn't just curious, they were emotionally moved, connecting to something primordial and vast in a way graphs and equations couldn't convey. Artists seized on the phenomenon almost immediately. Electronic musicians sampled the CMB's frequencies into ambient tracks, layering them with pulsing synths to create what one producer dubbed cosmic techno. Visual artists paired the sonifications with swirling, abstract animations, turning the universe's vibrations into multisensory experiences. Perhaps most striking was a live performance by the London Philharmonic, where the orchestra played an original composition inspired by the CMB's acoustic peaks, their strings and brass mirroring the density fluctuations of the early universe. The concert sold out within minutes, proving that science, when framed through creativity, could captivate audiences as powerfully as any symphony. Media outlets amplified the cultural moment, but not without hiccups. Some headlines oversimplified the science, claiming we'd recorded the Big Bang sound, ignoring the complex translation process involved. Late-night shows jumped in too, with hosts joking about the universe's bad Wi-Fi connection or comparing the CMB's drone to the world's deepest didgeridoo. Yet even the jokes served a purpose. They made cosmology approachable, sparking conversations in living rooms and coffee shops about inflation, redshift, and dark matter. Museums noticed, too. The Griffith Observatory in Los Angeles debuted an interactive exhibit where visitors could remix the universe's sound waves by adjusting sliders for dark energy and matter, watching in real time as the harmonics shifted. Kids left wide-eyed, finally grasping how the cosmos ingredients shaped its voice. Social media platforms became laboratories for collective interpretation. TikTok videos superimposed the CMB's sound over footage of crashing waves or forest landscapes, creating viral vibes that blurred science and spirituality. On Instagram, astrophysicists hosted live Q and as while playing the Sonifications, demystifying the data behind the noise, but the most unexpected response came from religious communities. Pastors wove the audio into sermons about creation. Buddhist monks compared it to the Om chant, a vibrational echo of the universe's unity. The sound transcended disciplines, becoming a rare cultural touchstone that scientists, artists, and spiritual seekers could all claim as their own. Yet beneath the wonder lay a subtle tension. Some cosmologists worried the Sonification's popularity might eclipse their scientific purpose, reducing painstaking research to a viral novelty. Others argued the opposite, that public fascination could fuel support for future missions, like the Simons Observatory or CMB-S4. The debate revealed a deeper truth: science doesn't unfold in a vacuum. When the universe's oldest vibrations became a shared cultural experience, they didn't just educate, they reminded us that discovery is a dialogue, one where data and humanity's thirst for meaning constantly intertwine. The world didn't just hear the CMB, it listened, interpreted, and made it part of our collective story. Want to decode the universe's vibrations without a billion-dollar telescope? The cosmos isn't just for professionals with free tools and a little curiosity. Anyone can turn astrophysics data into cosmic soundscapes. Start with NAS, a cosmic microwave background sonification project, where raw temperature maps from the Planck satellite are pre-loaded into beginner-friendly software like Audacity. Just drag the data file onto the timeline, adjust the speed to shift those deep primordial hums into audible ranges, and suddenly you're listening to the afterglow of the Big Bang. No coding required, just an ear for patterns and a willingness to experiment. For those craving hands-on challenges, platforms like Universe Sandbox let you simulate galaxy collisions, then export the gravitational wave signatures as WAV files. Imagine tweaking the mass of two merging black holes and hearing how their chirp deepens as you increase their size, a visceral lesson in Einstein's relativity. Over on GitHub, open-source repositories like Sonify provide Python scripts that transform telescope datasets into MIDI melodies, where distant pulsars become rhythmic drum loops and solar flares morph into glitchy synth stabs. One amateur in Finland used these tools to compose an entire album from radio emissions of the Whirlpool galaxy, proving science and art aren't so far apart. Teachers and students can dive into Zooniverse's Radio Meteor Zoo, classifying meteor echoes in radar data that, when sonified, sound like pings in a submarine sonar. Each confirmed detection helps calibrate models of how interstellar dust interacts with Earth's atmosphere. Or try the Sloan Digital Sky Survey's Galaxy Explorer, where you can assign musical notes to galaxies based on redshift higher pitches for faster-moving clusters, lower tones for slower ones, revealing the universe's expansion through melody rather than graphs. The most thrilling frontier, real-time cosmic noise. Apps like Space Audio Stream tap into live feeds from radio telescopes like the Allen Array, letting you eavesdrop on Jupiter's magnetosphere or the Sun's plasma waves while they happen. One couple in New Mexico even hooked up their backyard telescope to their min, turning fluctuations in stellar brightness into eerie, improvised space music during meteor showers. What makes these projects so powerful is their democracy. When a teenager in Mumbai sonifies quasar data and notices an unusual harmonic pattern, professionals take notice. Some of the most cited papers in Astro-Coustics now include discoveries from citizen scientists. The universe's soundtrack isn't locked behind academic gates. It's floating in open data repositories, waiting for fresh ears to hear what others might have missed. So whether you're a musician, a coder, or just someone who loves stargazing, remember, the cosmos has been vibrating for billions of years. Now, thanks to technology, it's finally your turn to listen. Cosmic sound research doesn't happen in isolated labs. It's born from collisions between wildly different worlds. Picture a room where a quantum physicist debates musical theory with a jazz composer, while a data scientist tweaks code that translates galaxy rotations into harmonic scales. This is the reality of modern astro-acoustics, where breakthroughs emerge from the friction between disciplines that rarely speak the same language. Take Dr. Grace Wolfe Chase, an astrophysicist who partnered with the Chicago Symphony Orchestra to sonify star-forming regions. By mapping infrared data from the Spitzer Space Telescope to orchestral instruments, warmer dust clouds as cellos, younger stars as piccolos, they created a piece where the birth of stars became a literal symphony. The collaboration revealed patterns in stellar nurseries that traditional graphs had missed, proving that sometimes you need a musician's ear to hear what equations can't show. On the tech side, programmers are building bridges between cosmic data and human perception. At MIT's Media Lab, a team designed Astrosonic, an interface that lets users play the universe like an instrument. Load a dataset of pulsar frequencies, and the software maps them to a modular synth where knobs control parameters like redshift or dark matter density. Twist a dial, and you're not just adjusting numbers, you're hearing how the cosmos would sound if inflation had lasted a microsecond longer. These tools aren't just for scientists. Electronic artists like Holly Herndon have used them to generate otherworldly tracks, blurring the line between research and performance art. The magic happens in translation. When mathematician Dr. Jana Levin worked with composer Nico Mulley on Dark Matter, a chamber opera inspired by gravitational waves, they faced a fundamental challenge: how to make space-time ripples emotionally resonant. The solution: treat LIGO detections like a musical score, with each black hole collision triggering a percussive event in the strings. The result wasn't just aesthetically striking, it helped audiences viscerally grasp the scale of cosmic violence. Similarly, the Sonification Universe project enlists sound designers to create customizable audio representations of exoplanet atmospheres, turning atmospheric pressure graphs into shimmering pads or rhythmic clicks that hint at alien weather patterns. These collaborations are rewriting how science communicates. At Stanford's CCRMR, researchers and composers use spectral analysis, a technique borrowed from music theory, to identify harmonic structures in quasar emissions. Elsewhere, bioacoustics experts apply methods developed for whale song analysis to decode the pulses of magnetars. The cross-pollination goes both ways. Algorithms created to clean up cosmic microwave background noise now help audio engineers remove hiss from vintage recordings. What unites these efforts is a shared belief: the universe doesn't divide itself into art and science. Its vibrations obey mathematical laws but stir human wonder. When a pianist improvises over a sonified supernova remnant, or a coder turns galaxy clusters into a generative MIDI sequencer, they're not just interpreting data, they're continuing a tradition as old as humanity itself. From Pythagoras to Planck, we've always listened to the stars. Now, thanks to these boundary-smashing collaborations, we're finally starting to understand their song. The hum of the early universe might sound like a single, unified story, but beneath the surface, cosmologists are locked in spirited debates over what those primordial vibrations truly mean. While the standard model of cosmology ties cosmic sound waves to inflation and dark matter, rival theories offer radically different interpretations. Take loop quantum gravity, which suggests space-time isn't smooth but granular, woven from tiny, indivisible loops. In this framework, those early sound waves didn't propagate through a continuous medium but hopped across a quantum foam, leaving subtle distortions in the cosmic microwave background. Supporters point to anomalies in the CMB's large-scale polarization patterns as potential fingerprints of this pixelated space-time, like hearing static in a recording where others hear only silence. String theory takes the controversy even further. If the universe's fundamental building blocks are vibrating strings rather than point-like particles, those first cosmic notes could carry echoes of extra dimensions curled up at microscopic scales. Some models predict resonant frequencies in the CMB that standard cosmology can't explain: harmonic overtones from strings stretching across hidden spatial folds. Detecting these would be like finding a guitar string's vibration still humming inside a sealed box billions of years later. Critics argue these ideas stretch plausibility, but proponents counter that the universe's harmonics already defy classical intuition. Then there's the Big Bounce hypothesis, which replaces the Big Bang with a cyclical universe that collapses and rebounds eternally. In this view, the acoustic peaks in the CMB aren't just from inflation, they're artifacts of a previous cosmic cycle's death throes, like grooves on a vinyl record pressed from older, forgotten music. The theory predicts faint, secondary oscillations in the CMB's power spectrum that mainstream models don't account for. While current data lacks conclusive evidence, upcoming telescopes like CMB-S4 could settle the debate by either spotting these ghostly echoes or ruling them out entirely. Even within mainstream cosmology, tensions simmer. Some researchers argue that the observed damping of certain sound wave harmonics points not just to dark matter's influence, but to entirely new physics, perhaps sterile neutrinos or action-like particles, subtly interfering with the primordial plasma. Others propose that what we call sound in the early universe might be better modeled as turbulence, with chaotic vortices leaving fractal-like patterns in the CMB. These dissenters aren't fringe thinkers, they're respected scientists pushing back against what they see as overconfidence in the standard model's completeness. The stakes are higher than academic squabbles. Each competing theory implies a different fate for the cosmos. If loop quantum gravity's granular spacetime is real, the universe's expansion might eventually reverse. String theory's extra dimensions could mean parallel universes vibrate alongside ours, They're unseen frequencies subtly tweaking our own. And if the big bounce is correct, today's cosmic microwave background is just one movement in an infinite symphony of cycles. What unites these divergent voices is a shared recognition. The universe's first sounds aren't just relics. They're a battleground for humanity's deepest questions about reality's fabric. Every anomaly in the data, every unexplained harmonic, is a potential crack in our current understanding and an invitation to listen more closely. After all, science doesn't progress by consensus alone. It advances when someone dares to hear a different melody in the noise. Dr. Brian Greene once said that science isn't just about equations, it's about the people who chase them. Few embody this truth like Dr. Amber Miller, who spent 20 years hunting for whispers from the Big Bang in the most inhospitable place on Earth, Antarctica. Picture her there, bundled against -70-degree winds, calibrating a telescope at the South Pole to capture the cosmic microwave background's faintest fluctuations. It's like trying to hear a pin drop during a hurricane, she admits. Her breakthrough came not in a eureka, a moment, but through stubborn persistence after a decade of failed experiments. Her team finally isolated the acoustic signature of primordial sound waves buried in the static. What kept her going? The data wasn't just numbers. It was the universe's oldest lullaby, and I needed to hear it clearly. Then there's Dr. John Kramer, a physicist turned accidental composer. While modeling the early universe's quantum fluctuations, he realized the equations describing sound wave propagation were eerily similar to those in his weekend hobby synthesizer programming. On a whim, he translated CMB data into an audio file. The result, a deep, resonant drone that made headlines as the sound of creation. Colleagues dismissed it as a gimmick until astronomers pointed out the harmonics matched predictions for inflation's energy scales. Science doesn't always wear a lab coat, he laughs. Sometimes it wears headphones. For Dr. Nergis Mavalvola, the cosmic symphony became personal through gravitational waves. As a key figure in LIGO first detection, she describes the moment they heard two black holes collide, a faint chirp after 40 years of silence. That sound was proof Einstein was right, but also so much more, she reflects. Growing up in Pakistan, she'd trained as a classical pianist before physics stole her heart. Music taught me to listen for patterns. When that chirp came through, it wasn't just data. It was the universe going ta-da. The challenges these pioneers faced weren't just technical. Dr. David Spergel, who led the Planck satellite's data analysis, recalls the pressure of debunking his own team's findings. When early results seemed to confirm controversial dark flow theories, he spent sleepless nights rechecking the math only to trace the anomaly to galactic dust. Science isn't about being right, he says. It's about being honest even when it hurts. Perhaps the most poignant story belongs to Dr. Rachel Somerville, who turned to cosmology after losing her sister to cancer. I needed to believe in something bigger than pain, she shares. Her work on acoustic oscillations in galaxy clusters revealed how sound waves shape cosmic structure, but her motivation runs deeper. When I map those ancient vibrations, I'm not just studying the past. I'm seeing how chaos becomes order, how randomness creates beauty. That's not just physics. That's hope. These aren't just researchers. They're interpreters of a cosmic language, translating vibrations across billions of years into human understanding. Their stories remind us that behind every dataset, there's a person who stayed up late, doubted themselves, and kept listening not just with microphones, but with hearts wide open to the universe's oldest song. The sound of the early universe isn't just a whisper from the past, it's a living thread connecting us to the very moment everything began. Think about it. Those primordial vibrations, frozen in the cosmic microwave background, are the same fluctuations that seeded galaxies, stars, and ultimately, us. Every time scientists translate those ancient waves into sound, they're not just replaying history, they're giving us a chance to eavesdrop on creation itself. It's humbling to realize that the same physics that orchestrated the universe's first notes also shaped the atoms in our bodies, the planets in our solar system, and the vast cosmic web we're still mapping today. What makes this discovery so extraordinary isn't just the data, it's how it reshapes our perspective. For centuries, we've studied the cosmos through telescopes, capturing light from distant stars. But sound adds a new dimension, literally. When we listen to sonifications of the CMB, we're experiencing the universe through time as well as space, hearing how those vibrations stretched and evolved over billions of years. It's like finding an old recording of your grandparents' voices, except this recording predates humanity, Earth, even the first stars. Suddenly, the Big Bang isn't an abstract concept. It's a vibration you can feel in your bones. And this is just the beginning. As technology leaps forward, we're on the brink of hearing even fainter echoes, gravitational waves from inflation's first trillionth of a second, quantum whispers from before space-time as we know it existed. Projects like the Simons Observatory and next-generation space telescopes promise to sharpen our cosmic hearing, revealing harmonies we can't yet imagine. Who knows what secrets those sounds will unlock? Perhaps they'll confirm the existence of parallel universes or expose flaws in our understanding of dark energy. Whatever they reveal, one thing's certain: the universe's soundtrack is far richer than we've ever dreamed. But here's the most beautiful part: this isn't just science's story. It's yours. Every time someone listens to the sonified CMB and feels that chill of connection, or shares their own artistic interpretation of cosmic data, they're adding to humanity's collective understanding. The universe has been singing for billions of years, and now, for the first time, there are ears to hear it. So tell me in the comments, what does the universe's voice sound like to you? A chorus, a heartbeat, the hum of something vast and mysterious. And if you're hungry for more deep dives into space's greatest mysteries, hit subscribe. The cosmos has plenty more to say, and I'll be here to help translate